So far, we learned about the Trump problem, which is essentially about how we can find the copy of H in G as a subgraph. So finding H in G as a subgraph, it's the same as finding a map, say F, which maps the vertices of H to vertices of G, such that what? All the edges are mapped to edges. F of U, F of B are edges in G, or edges in H. So for example, if G is like this, and then if your H is this, then you map this vertex to here, and this vertex to here, and this vertex to here, and this vertex to here, then that's same as finding a copy of C4 here. So edges are mapped to edges, but the non-edges does not have to be mapped to non-edges. Moreover, we need one more condition, that F is injective. Otherwise, if you map two vertices to the same vertex, then it's not C4 anymore that we found. So that was what we have been dealing with. But there are also other types of structure that we can consider, and one of them is about homomorphic copy of H. In other words, graph homomorphism. So we will talk about graph homomorphism. So what's graph homomorphism? So sometimes, this kind of map are called as a graph embedding. So embedding of H into G. And sometimes if we just want to a bit relax on this condition by deleting this injectivity condition, then the problem often become easier and we can find more tools to deal with. And that's what's called a graph homomorphism. So we want to find a map which satisfies the first condition. So let's say for graph H and a multigraph G, you consider a map which maps the vertices of H to vertices of G is a graph homomorphism. If, again, all the edges are mapped to edges, it holds for every pair UB which are adjacent in H. We write hom HG to denote a set of all homomorphism is to G. And for this specific F, the subgraph of G, which is F of H, which has a vertex set F of BH and the edge set. This is called a homomorphic copy. Of H in G. And if this homomorphic copy of H, which is not isomorphic to H, which means that if F was not injective, then its image is called a degenerate copy of H. So in the above case, what could be the case? If we map, say, this to here, if this was red instead, then this is still homomorphism, and that homomorphic copy is this one. So this maps to here, this maps to here, this maps to here. This edge maps to here, this edge maps to here. So this is a homomorphic copy of C4. And then this is a degenerate copy. So, and this graph homomorphism is useful in several ways. So one of them is, as I mentioned, this is a relaxation of this binding subgraph problem. Instead of binding H inside of G, we can consider its homomorphism. Then we can find the homomorphic copy of H in G. So that's one relaxation. So in other words, it's a tool to study about graph G, whether it contains certain copy as a subgraph or not, as a subgraph or as a homomorphic copy or not. But there are more ways that this homomorphic copy is useful. And sometimes it's used to study about the graph H instead of G. For example, this, what does it mean? So if we have a graph, say, G, let's just use H to make it more consistent. And let's say you consider the set of all homomorphism from H to K sub K, complete graph on K vertices. Then watch this. If this is not empty, it means that chromatic number of G is at least at most K. So this is essentially same as K coloring, set of all K coloring of H, proper K coloring. Why? If you have some graph H, and then you have a copy of KK, and you consider all the inverse image of each vertex. It has inverse image, so it's pre-image, and those pre-images have to be an independent set because we want the edges to be mapped to edges. And this vertex to this vertex, there is no edge. There are no loop here. So each of them are independent set. Each of them has pre-image as independent set. And conversely, if you have a K coloring, then you can map each set to each vertex. Of course, I mean, there are this like commutation of the color, but up to that, this is essentially same as the set of all proper K coloring. And also we can consider this graph. So there is two vertex A and B, and then there is H between them, and then there is a loop at B. Recall that we defined it for multigraph H. And what? This, if you just count this, and that's same as the number of independent set in H. Why? Again, you consider all three images of this vertex. We don't really care about what vertices are mapped to be. No matter what vertices are mapped to there, it's okay. It doesn't cause any problem, because even if there are edges here, because of this loop, it's allowed to map there. The only restriction here is that the preimage of A has to be an independent set. So whenever we have an independent set A, then you can find the homomorphism from H to here, which maps exactly A to here and then less to B. So this set has a one-to-one correspondence with the set of independent sets in H. And also you can consider the key vertex path. And then you consider all the homomorphism in there, then that's same as the set of blocks of length k minus 1. And the list goes on. There are many relations with this homomorphism and other graph theoretic concepts. Okay? And for this, for our motivation, the reason why this graph homomorphism is useful is once we forget about this injectivity, and often we are able to do more analysis using some analytic tool like Cauchy-Schwarz inequality. That helps us to find the homomorphic copy of H in G. And then if we can show that there are many homomorphic copies of H in G, and then we can somehow show that at least one of them is non-degenerate, then we are succeeded in what we want. So that's roughly what why this is useful, and then why we, consider homomorphism. Okay, before proceeding further, and we will use this concept to find the bounds on the extremal number of even cycle. And that's our goal. But before doing that, let me introduce this concept of homomorphism density. So you count all the homomorphism from H to G, and then you divide it by this number. The number of vertices in G to the number of vertices in H. So what's it? This is the possible the number of all maps from H to vertex of H to vertex of G. And then this is homomorphism, the number of homomorphism. So this is called the homomorphism density of H in G. In other words, this is the probability that a map, a randomly chosen map, which is chosen uniformly at random, here is a graph homomorphism. So this is the one probabilistic interpretation of this homomorphism density. And regarding this homomorphism density, there is this famous conjecture called the pseudo-Rancourt conjecture. It said that if H is bipartite, well, then for any G, its homomorphism density is at least the homomorphism density of edges to the number of edges in H. And if you think about this, what's this? This is specifically this T K to G is what? So for each edge, there is two ways to embed this K2 to G. So A and B, then for each edge, either A goes to here, B goes to here, or B goes to here, A goes to here, to be a homomorphism. So that's like 2 times E of G divided by N squared. Okay. Then, this here is that when we take this as P, and you consider the random graph G and P, then you can compute the expected number of edges here. And you can consider the expected density, expected number of homomorphic copy of K2, then you would get this number. And here you also compute the expected number of homomorphic copy of H. Then, because this is random graph, you can actually compute it, and this is the number that you get. Simply, you have a, say, I don't know, H here, and the probability that this edge is there, this edge is there, this edge is there, this is there in this random graph is p to the 4. Of course, you have to do that for all n to the 4 choices. I mean, if you are consider a homomorphic copy, it's not n to the 4 choices, n to the 4 choices. And then you have to consider the permutation. But anyway, for each one, the probability that it becomes actual homomorphic copy is p to the 4, and then p is this one. From there, I mean, this is exactly the number of homomorphic copy of H in the random graph. In other words, this shows this says that or I mean, in other words, this conjecture, what it essentially said is that among all graphs with fixed H density, if is minimized when G is a random graph. And this is only for bipartite graph because it's not true for general graph. For example, if H is K3 triangle and G is a complete bipartite graph, Kn over 2, Kn over 2. Then what happens? Then you have 0 here. And on the right-hand side, you have a positive number. So this doesn't work. So it only holds for bipartite graph. And this conjecture is open. There are some graph classes. I mean, it's known that this holds for some graph classes. For example, if H is trees or even cycle and some other graph. But in general, this is wide open. The smallest graph that we don't know the answer is, I think, K by 5 minus perfect matching. So this graph is, still not known. Sorry, not perfect matching. I got confused. Minus C10. So you have these are all non-edges and everything else are edges. So you have 5 vertices, and then these 10 edges are missing, and then the rest of them are edges between them. So that's the smallest graph that this conjecture is not known. Okay, so we can actually prove this for even cycle. So this conjecture is true for even cycle. So let's say GB on n vertex bipartite graph. Okay, so we will prove it for the case where G is only bipartite, because this lemma will be useful for us later to prove the boundary on the extremal number of even cycle. So let's just prove this conjecture when H is even cycle and G is also bipartite graph. So this is a bipartite graph with vertex partition AB with say average degree is n for every k. We have the following lower bound on the number of homomorphisms of C2k into G, which is the average degree to the 2k. So if you divide both sides by n to the 2k, then what? This is dg over n to the 2k, and then that's same as what? 2e of g divided by n squared 2k. So this is same as the homomorphism density of k2 in G. So this actually showed the Sidorenko conjecture when H is an even cycle and then G is a bipartite graph. What we do, we consider the following graph. The bipartite adjacency matrix M, where this is indexed by the A and B, and then this is either 0 or 1. So this is 1 if, so let's say Mij is 1 if Ij is an edge in G, 0 otherwise, where I is the vertex in A and then J is the vertex in G. Then what happened is that you consider this graph. I mean, this matrix. So what's this matrix? This matrix is indexed with B on the row and column as well. And what? This is one. No, not necessarily one. This is the, let's say, it's ij entry counts the number of blocks of length 2 from I to j, where ij are both in B. Then what we know? The homomorphism C2K, homomorphism of C2K in G is same as you start from somewhere and then you come back. So what's this? This is what? In this metric, you start here, then you move, then you move, and then you move, and then you come back. So that says that's same as you take this matrix and you take the case time, and then you add all the diagonal entries, and that's the trace. So trace of this case power. And we know that this is same as lambda 1 to the k to the plus lambda 2 to the k plus dot 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 lambda m to the k, where if n is same as size of b, we just define it this way. And this lambda 1 and lambda n, m, are the eigenvalue of this matrix. So, and furthermore, we know that this is a semi-definite matrix, M transpose M. So these are all non-negative number. Okay, and we have this. Then these are all non-negative. So this is the biggest term out of this. If some of them are negative, then it could be, the square could be bigger than lambda 1 square for all we know. But I mean, this is semi-definite, so all of them are non-negative. Then what we know is that the Coulomb-Fisher theorem, which is well-known theorem. So we also talk about this in the introduction of the graph theory. This states that the lambda 1 is same as the maximum of all you consider all vector in R to the n. Okay, let's just write x. And x transpose mx divided by is a Rayleigh quotient. And we know this. And from here, what do we know? By taking x as the all one vector, then because of this maximum condition, this lambda 1 is n most the Rayleigh quotient of this 1, 1, 1. So 1, 1, dot, 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 1, m transpose m, 1, 1, 1, 1, 1. And you do that m, this is n. m, sorry. And what does this count? This counts, say, from each vertex B in here, so you count this K1, 2. But that can be counted in another way, that you focus on this middle vertex. For each middle vertex, you consider the degree square, then you count this. Remember that this is also counted as in terms of this B. So here, I mean, here from one vertex to the other vertex. And here, this is also counted. So this exactly counts what we want. And you divide by B. But using Cauchy-Schwarz, what's this? This is a lit. You take out the square and then divide by side of A and side of B. And this is a lift. We know that the side of A plus side of B is almost n. So this is maximized here. And the above one is the number of edges square, so which is the average degree square. From this, what we know, here is at least lambda 1 to the k, which is what? At least the average degree to the 2k. That's exactly what we wanted to. Okay, so we have collected this. And now we collect one more thing, which is the following lemma, or the regularization lemma. So oftentimes we study about this extremal number, and then we want to throw an upper bound. And what we have to do is, when the number of edges is something, we want to find a copy of H in G, when G has many edges. But if we have no information about the structure of G, it's difficult. So we want to find some property of G first. We want to ensure some things that we know. And one of them is that we can actually assume that the minimum degree and maximum degree of this G are not too far apart. So let's say you have this graph G, and assume n is large, and then epsilon and C are given. If G satisfies, okay, technically, I mean, yeah, this 1 over C does not have to be smaller than 1, but if G satisfies that, so it has at least C times n to the 1 plus epsilon h, then if G contains an m vertex graph, say H, with this m being not too small, so it is n to the this number, and number of edges in H is almost similar, 2 over 5 times C times m to the 1 plus epsilon. You see, so here it's the number of edges to the 1 plus epsilon. Here again, the number of vertices to the 1 plus epsilon, and number of vertices to the 1 plus epsilon. The constant is a bit worse, but essentially, I mean, it's similar, where the maximum degree of this is at most 100 times 2 to the 1 over epsilon square times the minimum degree of H. So H is almost regular in a sense that the minimum degree and maximum degree are off by multiplicative constant. while doing that, if H is a subgraph of G, which is not too small. So often how we can use it is that if you want to show that extremal number of say F and F is say, we want to show that this is big O of n to the 1 plus epsilon. This is what we want to show. Then what do you have to do? We have to do that G with some constant times n to the 1 plus epsilon. What contains is F in G. But this G, we don't know much thing. So what we can do is we find the H, which is subgraph of G, and it also satisfy, like this condition where M is the number of vertices in H. And it has additional condition that its maximum degree and minimum degree are not too open. So instead, if we find the F in H, then that automatically give us the F in G. So instead of just proving this, it suffices to prove existence of copy of F in H. In here, H has additional advantage that we know this one more condition that we can use to write. Yeah. So this is a regularization lemma. And roughly how can you prove this? I will just do the proof sketch. I will not do the computation. Let's say P is some large number, P2, 2 to the 1 over epsilon plus 1. And what we do? If we have G, we partition the vertex set into B1, B2, B2P of almost same size. So that the all largest degree vertices are here. And then next largest degree vertices are here. So this is partitioned according to its degree. And then smallest degrees are here. And what you check between here, you count the number of edges between them. If the number of edges between are like small, if it's less than half of the E of G, then what? Then delete B1 and repeat. No, sorry. No, sorry. You delete B1 and delete vertices with 2 row degree. So as I mentioned, all the largest degree vertices are here. And then this is constant fraction. So once you delete this, you no longer have no vertices with a too high degree. And by deleting this, now you might introduce vertices with too low degree, but you can just delete them. That will produce a desired graph. It's not too difficult to actually check it. And if this one is bigger than half of E of G, then what you do is that you choose J such that the B1 and Bj, the number of edge between is at least 1 over 2p E of G. Sorry, the 1 over 4p. Okay, so if let's say originally we we partition it to P of them, and this is 1 over 2P. So the number of edges are, let's go to the original way. Then what happened? Then the number of vertices in this new graph were divided by n over 2p. And the number of edges were divided by 4p. I mean, at most 4p. Okay, and yeah. And then with this new graph, you start from the beginning. Again, now in this graph, you divide it into 2p sets. And then you check whether this apply or this apply, and you keep doing that. At some point, you can show that at some point, the first case must happen. And then you will obtain what you desired. And then with some computation, you can show that that happens before this gets too small. And then for such graph, I mean, these conditions hold. Essentially, the reason why it holds is that so when this holds, right? So n becomes n over 2p, then n plus 1 plus epsilon becomes n plus this becomes this. Okay, but what? No, sorry, the number of edges. Let's write it this way. The number of edges, this becomes n to the 1 plus epsilon become it divided by 4p. But what's this? This is like n to the n over 2p to the 1 plus epsilon. You can show that this one is bigger. Why? It's about 2p to the 1 plus epsilon, and then 4p, what's the bigger one? And this is what? So this is essentially comparing this. Because of our choice, this holds, so this is bigger. So even if you see it, so this decreased by the 2p ratio, and this decreased by 4p ratio, and 4p ratio seems faster. But in terms of this 1 plus epsilon, I mean, if you keep in mind this exponent, then this inside, they shrink proportionally. So you repeat this, and then you reach at m, and it still has some appropriate constant times m to the 1 plus epsilon. It still has more than this many edges. Because, it decreases, and then it's decreased by this much, and then this is same as just putting the same number and then the same exponent. So that's why, I mean, this holds with the same exponent. And that's the motivation why we pick this number in this way. Yeah, I will not write the details of this proof, but that's the idea. Okay, now we have corrected this tool. In the next video, we'll prove an upper bound on the extremal number of even cycle.